Hello and welcome everyone to another webinar series from Amsterdam Data Science. This week we've partnered with the City of Amsterdam, the IF and the VU, and we're hosting a webinar on the implementation of AI in the City of Amsterdam. To quickly introduce myself, I'm Anita and I work with the ADS team. ADS is a network organization that seeks to promote and foster the data science and AI ecosystem here in Amsterdam. And we do that by connecting industry, academia, and society. And some of the activities that we're involved with are webinars such as these to provide people with more knowledge and insights in the field of data science and AI. So without further ado, I would actually like to give the floor to Maarten to start his presentation, and he can start sharing his screen.
Welcome, everybody. Great to have so many people here interested to see what we're doing with AI for Amsterdam. So to start with, as mentioned by Nina already, we're starting today with a small overview, and then Daan is going to dive a little bit more into a really nice point cloud project we're doing. Afterwards, we will give the microphone, digital microphone to Eva, who will be introducing some very interesting talks about some thesis research that's been going on at the city during COVID, so all online, but very amazing and interesting work. So this is like the subjects we're going to be discussing, as I said, a bit of an overview of the point clouds, and then there's going to be 4 thesis research presentations. The first one is going to be about reinforcement learning for traffic light control. The second one is about using guns, if I can summarize it, to generate objects, which we at one day hope to use to generate new versions of the city that do not exist yet and have people give their opinion about it. So Tom, you will elaborate about it more, but that's a bit of how I envision it eventually being used. Then Kaleigh will talk about anonymizing people using guns. So instead of blurring people from image, we do blur them, but we also try to replace them with people that do not exist, which I think is very interesting use of guns, and also creates a lot of interesting questions like, does somebody that doesn't exist actually have the right to privacy? We will end with our last speaker, Selma, last but not least, who's working on a model agnostic method for detecting bias in these models. So also very interesting. So here's a bit more like images of what's to come. So a bit of a sneak peek to get everybody excited. And I will continue to the next one now. So why are we investing into AI as a city? We came up with the AI agenda. So basically what we say is we want to stimulate the use of AI because we think it's going to be very, very helpful for our citizens, but also for the city as a whole. But at the same time, we are aware that AI technology does also have certain risks. So we want to basically optimize all the good things and minimize all the bad things, if you put it really simple. We want to achieve this by investing in AI R&D. We also want to be really transparent about the project. So having talks like this, and eventually we want to basically get all our data sources out, get all our methods out, so everybody can give input on it, and also mention it when we're doing things that might not be exactly what we want. We also want to scale urban AI solutions. So we want to try to get as much people positively influenced by these projects eventually. But the core goal would be making AI work for the citizens, which I realize is not really a how, but basically that's how we're going to have the positive impact, is by having it work for the citizens and not against them. So also, of course, as a city, we have certain goals. So, of course, during COVID, we want people to be safe. We want people to feel free in the city and to feel safe in the city, but we also want a more sustainable city. So there's like a lot of challenges we have where we think AI can be a very beneficial element. So this is currently the AI team working for the city. So you will see some of us here, you will see some of us later, undoubtedly, working on some very interesting products. So data scientists coming from different universities, little bit different AI backgrounds. And of course, Claudia, who is our UX UI designer, which really helped us to make these nice images today. But we're not doing it just within the city. Of course, we collaborate with all the departments within the city of Amsterdam because it's an organization with more than 18,000 people. Last time I counted. We also want to work together with our partners. So today we're here together with students from the University of Amsterdam and the VU, but we also work together with, for example, the ICAI, we have the Civica iLab, we have the new AI for People branding we're giving to Amsterdam, also working together with different government institutes to basically work together on creating this technology for cities. So in one sentence, what we will be showing a little bit of today is how we plan on using state-of-the-art AI research today to increase the livability of the cities of tomorrow. So I'm going to start with this image of this creature, which I found is the first creature with eyes. We lived 540 million years ago, approximately, give or take. And this is a video of panoptic segmentation going on the streets of the city, where you can see, even if the model is not optimized for this specific video, it's already the results are being pretty good. So the advancement of AI is not something that can be ignored. And even with the computer vision has been going really fast over the last years. So if you compare that, like the 514 million years ago to the recent decades in which this really has been advancing, well, you can see how fast this is going. So we really have to be on top of this as a city. So as I said, also cities are changing. So we want more equality, be more sustainable, and the population is growing. We have challenges such as COVID. So there's a lot of challenging things going on. So an example of a challenge we have is, of course, everybody now ordering their products online, causing a lot of cardboard. Containers were never designed for this amount of cardboard. So there will be bulky waste and household waste all over the streets. And people will report these using like service requests, and we will go there and try to clean it up. But the scale of it is so huge, and waiting for somebody to basically say, hey, there's something on the road, we're already too late because it's already a nuisance. And also an issue with these service requests is that in some areas, a lot of people know how to find us and how to contact us, and we will be more aware of any issues there. In some areas, people are less tech savvy, or you simply do not have time to make these notifications for whatever reason, which will cause a certain imbalance in the street. So we thought with this new, the possibility of computer vision, can't we try to create something that basically scans these? So we made a system called the Object Detection Kit, which was basically smartphones attached to dashboards, which we tested for a few months last year, to see if we can make such a system, to collect data about basically real-time street level imagery to see, hey, what's on the streets. And we would make models like this that are detecting garbage bags or the poles, construction containers, and try to align that with like our garbage department. Like, hey, this street is pretty trashy, as you can put it, or there's a construction going on here. What can we do with that? As you can see in this videos, the filter already got much better with the work of Lance and Chris last year, but it's already removing out the license plates, which shows that we really want to care about privacy. We also improved the people filtering here. Now we're going for the whole person, which is a lot easier. So you could use such a system, of course, to see where the trash is, but you also can change the whole way you organize such things. Because if we can know where furniture or where wood is, we can collect it separately, turning it into resources instead of trash. So that's also making everything more sustainable, but of course also more efficient. So there's less emission of our garbage trucks. And that all really adds up. If you're talking about 50,000 container locations, we have to make sure they're clean, for example. Well, that's a lot of locations we have to hit. So the more information about which ones are dirty and how dirty they are will really help that. And of course, you can think about monitoring our assets, like, hey, are they polluted with, for example, with graffiti? Can we clean that? And thinking about like, well, a cleaner city gets better behavior, makes people more tidy, and eventually will also save a lot of costs. So those are all things we're like researching. Hey, can we detect that? And how do people think about this? Does this make people basically more happy or more sad? And will it make the city more livable? So if you want to know more about the Object Detection Kit, you can find it on the website. It's odk.ai. And yeah, there's another project. So we have a lot of, we used to have open data of the panoramic images, but we were using a bit of an old personal privacy filter, which is now updated. And we hope to publish these images once again with, basically the advancement we have it over the last years, both on the side of how privacy-proof you have to make images before you can make them public, and how well the filters work. Right now, the filter, again, works well enough to be able to just distribute these images of the whole city, which I think is used for a lot of interesting research. Another core thing that we are aiming to do more and more is putting all our algorithms on the algorithm register, which is basically going to be an overview of all the algorithms that the city is using. It's really something we got a lot of interesting feedback on, like you should add more information. So we try to upgrade that, whenever we build something and wherever we add algorithms and change them. But a lot of people find it really interesting to see, hey, what's going on in the streets with algorithm? What is deciding about my life right now? And how is that decision being made? Of course, for some things you can be completely transparent. But if you're detecting fraud, for example, you might not want to give away all your features you're using for this detection. But it's a work in progress. But I think it's a really nice initiative, being like the first step to being truly compliant as well to the new EU regulations coming up. So some other projects, I won't go in full detail, but of course during COVID, we did a project with the 1.5 meter. So basically it's object detection and then some simple matrix calculation to see how close are people to each other. It's a bit like a social distancing awareness tool, but it was also a way of seeing, hey, how can we put up a camera in a public space and what is required for that, like on a legal side of things, and how are people responding to this such screens in the public environment. Another one we're doing it's called the public eye system, where we want to build an open source tool for crowd counting, basically knowing, for example, how many people are in the Vondelpark right now or 1 hour ago, and eventually, use that data to see, hey, when do we have to close down the park when it's getting too crowded to prevent any incidents from occurring, social distance-wise or otherwise safety-wise. So, like a lot of interesting data sources that we can learn a lot from and gather information. So here you see like things we can do with just computer vision, with aerial photography or panoramic images. Also already very interesting that you can imagine the autonomous cars coming up the next years. Why don't we get all that information they're gathering and also use that for a more livable city? But a very interesting thing we're coming up to now is using point clouds of the whole city, basically for urban intelligence. And to talk about this subject, I first have this one more slide. So all these data sources are a new way to see the world, and we think we can use those for a more fair and sustainable city. And about one very interesting data source, I will now give the word to Daan. Daan, good to have you.
Thanks, Maarten, and also thank you, Anita, for the introduction earlier on. So hello, everyone. Thanks for joining. My name is Daan Bloembergen. I'm recently joined the City of Amsterdam as an AI researcher, and now my first project within the city is to, look at semantic segmentation of point clouds. And particular today, I'm going to talk about how we use data fusion to make our life a little bit easier in that respect. So as Maarten already explained, more and more data sources are available to us, and these 3D point cloud data in particular offer a lot of advantages and a lot of possibilities. So basically our project is a kind of a pilot project where we want to investigate what can we do with this data, how much can we do ourselves, how much information can we get out of these point clouds. So in the next few minutes, I will give you a brief overview of our current progress and how we are currently using this point cloud data to map the public space. So on the next slide, Maarten is handling the slides, so I have to inform him every now and then. The City of Amsterdam recently acquired the street level point cloud of the entire city. You see a little example here on the image. Basically, the data was collected using a laser scanner and RGB camera mounted on top of a car. This means we have very high resolution at the street level, but less detail for higher objects or building roofs, as you can also clearly see in this image. The ultimate goal of this project is to automatically map the public space and to also create an accurate register of assets, such as street lights, traffic lights, trees, maybe even road parts, etc. And this will help the city, for example, with doing more targeted maintenance. For example, if citizens inform the municipality that a certain traffic light or street light is broken, then the city has to figure out which exact object this is and send an engineer to fix it. And if the data set basically is containing inaccuracies in the location, then you might send an engineer to the wrong street light, and this causes inconvenience. Also, if you would capture these point clouds on a regular basis, you can map out changes over time. And you can, for example, see that a tree might start to grow a little bit crooked, or a street light might be, being hit by a car at some point. A main issue that we have when working with these point clouds is the lack of labeled training data. So if we want to train, for example, a deep learning-based semantic segmentation model, we need lots and lots of training data. In contrast to, for example, 2D computer vision, 3D data is both sparse and non-uniform in its density, and this also makes it very hard to translate trained models from one data set to another. So on the next slide, what we're going to look into is how we can use large amounts of data that we actually have regarding the public space, such as elevation data, the registry of buildings, roadmaps, etc., to already help us with pre-processing and labeling this point cloud data. This will also help with data reduction along the way. If we can, for example, filter out ground objects and buildings from this point cloud, then we have less points left for more complex classification algorithms to then be able to focus only on this relevant subset of the data that still needs to be processed. Just to give you an idea about the complexity, like point clouds of the whole city of Amsterdam are in the order of 2 to 10 terabytes, depending whether you can compress it or not. So the more data reduction you can do here, the better. So far, we have implemented methods to automatically label ground points based on elevation data, which we take from the AHN, or Actueel Hoogtebestand Nederland, as shown in the picture, where we overlay the elevation data surface on top of the point cloud. Gaps in the data that you can see here are caused by cars and other noise, so we need to use some additional pre-processing steps to smoothen the surface. Once we've done this, we simply label all the points within the point cloud that fall within a small margin of this elevation surface as ground. In addition, we can use the BGT, or Basisregistratie Grootschalige Topografie, which is the registry of large-scale topographical objects, to automatically label buildings based on their footprint polygons. Again, we simply label all points within the point clouds that fall within each polygon as a building. Additional processing is then needed to make sure that we also include protruding parts of the building, such as balconies and canopies, by carefully, like say, growing the labeled cluster. I will show a little example later on. So we believe data fusion basically is a great tool to make more sense of the large amount of data that we have. Public data sources can be used for more detailed labeling, such as road parts, water bodies, vegetation, trees, poles, etc. The picture here shows data that is available on the website bdoc.nl, where you can see the shapes of buildings, but you can also see locations of trees, streetlights, road parts, etc. Our pre-processing pipeline so far is written in Python and will be made available through our GitHub page very soon. So if you're interested in this work, please follow our GitHub page. Also feel free to contact me personally. And finally, let me show you a small demo of our results so far. In this animation, you can see a 50 by 50 meter part of Amsterdam Zuid near Vondelpark. First we label the ground, which you see as the green surface. Then we label the buildings in a slightly darker green. And what's left eventually, we will now label in gray, but these are the points we still have to process. But what you can see is that this approach already works quite well in filtering ground and buildings. And the next step that we want to take in this project is to start also filtering out the trees, because these are also a very big chunk of the points in the point cloud that we want to get rid of. And afterwards, we can then move on to smaller objects. So that's it for my part. Thank you for listening, and Maarten and I can now take some questions. So I give it back to Anita.
All right. Thank you very much, Daan and Maarten. That was a really, really interesting and amazing presentation. Thank you very much. That was very informative. There are a couple of questions, which I will ask now. So we have a question from Ramiro, and they would like to know, would the data from objects, count and type, will that be available for public usage?
Yeah, so that's about the object detection kit. Yeah, we aim to make all the detections fully public, because we think it's very interesting also for research in criminology, sociology, to see basically, hey, what's going on in the city. So we do aim to make those public. Right now it's still a test system, so sometimes we measure for a few months and it's not consistent yet to make it public, but it's eventually the goal of the project to do that. Yeah.
Great, thank you for that. Sabina would like to know, just curious, What is the level of privacy assurance? For example, is it blurred to an extent that no one can be recognized from the clothes associated with religious and ethnic identities?
Yeah, so for those panoramic images, it used to be like 5 years ago, it was just the face that was blurred. We now decided, like, both because it's probably easier to blur complete people, but also because of those concerns, like still being able to see the clothing. For example, if it's your neighbor and in front of your house, you might know that, hey, that's this person wearing this type of sweater all the time. So now we're blurring people completely. And I think later Kaleigh will also be showing some very interesting alternatives that might be possible for this. So, yeah.
Great. Jacques would like to know, has the city geospatially mapped streets, or are third-party providers used for underlying geolocations, e.g. Google Maps or OpenStreetMap?
Yeah, I can probably also answer this. This is related to the point cloud, I guess. So we use the publicly available BGT. This is a national registry of topographical objects. Each municipality is responsible for maintaining their part of this data set. So within the city, we can very easily make use of these geospatial data. This is all available through this website, bdoc.nl.
Great. And there's one more question here. Nico would like to know, how do you, as in Amsterdam, collect point cloud data?
Right. So at the moment, we acquired this entire point cloud from a company called Sukel Media, which provides this type of data. We're still looking into in the future how we can do this cost effectively, like if we want to do this on a bi-yearly basis, for example. We're still figuring out how to do this. It's in that sense, it's also a pilot project to see which provider for this data will be best.
All right. So let me just see this. Okay, so first a compliment, great presentation. They would like to know, do you also have experience with semantic segmentation of 3D point clouds, e.g. automatic labeling of street infrastructure, advertisements, and advertisements?
In 3D, you said, right? Yes.
Yes.
So at the moment, this is the first time within the city, as far as we know, we're trying to do this automatically. So this is really much a learning experience for us as well. And we've been doing a lot of reading in the scientific literature in terms of algorithms that are out there for automatic semantic segmentation. And one reason why we try to do this pre-processing and sort of semi-automated labeling of point cloud data is to generate a big enough training data set that we can then feed into these semantic segmentation algorithms. So this is definitely one of the next steps that we're going to look into.
All right. And I guess like a question that maybe follows up a little bit more is, to what degree is labeling objects in the videos an issue? For the garbage detection, for example, how much work is it to label the videos that are used for training a model? How much labeled data is required?
Yeah, so until now, we've been labeling data sets of about 5,000 images, basically to see, hey, how good can we detect things, and then pretty intensively. So we do it with bounding boxes for people familiar with computer vision. We did notice that for like for a lot of these garbage type of detections, it's pretty hard, and we need a lot of data because garbage is one thing that's always looking different because it's something that should not be there. So we're now aiming for training sets about 50,000 images, and we also hope to make these public eventually. So yeah.
Great. Another question, could you potentially recommend a point cloud tagging tool for machine learning?
Right, this is also a very important question which we've looked into. We've looked mainly into open source alternatives. There are many companies that provide services, but we haven't tried them yet. So, for example, what we found is that software called Cloud Compare is quite usable in terms of labeling at least smaller parts of the point cloud yourself. But yeah, one of the reasons also why we try to do all this pre-processing is that you don't want to label each individual point of the point cloud. So ideally, you would want to pre-process the cloud in order to first look at what are all the clusters of separate objects that there are, and then you can perhaps manually label each cluster immediately. But this is a very big issue in 3D data. It's not straightforward. There are pieces of software, but all come with advantages and disadvantages. But yeah, Cloud Compare is definitely one that you could look into.
Okay, great. I think we've got time for maybe one more question. So a question I see here is, how do you deal with the temporal inconsistency between the different data sets?
I guess this might be related also to point cloud data, but of course this counts for many data sets. In our case, for the point cloud, we're not so much interested in moving objects. We're mainly interested in things that are a little bit more long-lasting, like buildings and streetlights. So if you have a few months discrepancy, this might not be such an issue. Of course, if there's an area of the city where construction work is being done, you will have to deal with this a bit more carefully. But one of the reasons why we also are interested in using these point clouds is that if you can collect these multiple times a year, this will help us to keep the other registries more up to date. So this is one of the end goals where we would see this project going, but that's very much future work.
Okay, all right. Okay, I think that's going to be in terms of questions so that we have enough time for our other speakers as well.
So, hello everyone.
Good luck.
I'm indeed Eva. I'm also part of the AI team. And as Maarten already mentioned a little bit in the first presentation, we're going to hear now about our students. Every year at the city, we host in an organized manner about 20-25 data science and AI students doing their graduation research with us at the city. We've tried here to select 4 projects. I hope they're a bit interesting. The way I see it in my head, there's roughly 2 big groups of projects that we work on. The first group is the applied projects that we can essentially put to good use tomorrow, and they're going to make our lives as citizens better and easier and safer. And the first project we are going to hear about is a little bit from this group. So think about projects like predictive parking, predicting usage of social services, predicting crowds in the city. And the first talk we're going to hear about will be specifically about traffic. And I'm going to screen share now and give the word to Sierk, if he could maybe join me here. And please excuse any sloppy slide switching from my side. Enjoy.
Okay, thanks, Eva. Can you hear me well?
Yeah.
Loud and clear.
Very good. Okay, so I will talk a bit about my project, the AI team, which is about applying reinforcement learning for traffic light control. So traffic lights, you all know them, and you all know that you're waiting and waiting and waiting, and you don't sometimes you don't know why you're waiting for. So nowadays, there's so much more data available. Everyone has a phone in their car almost. There's so much GPS data. And nowadays, that's the other part, is that there's so many more artificial intelligence techniques available. I think everyone has heard about AlphaGo and AlphaZero that has beaten the Go world champion. And is also the best chess player in the world now, that's computer. Isn't it possible to use all these data together with all the new AI techniques to create a better and smooth flow of traffic through the city? So our goal for this project was to minimize the travel time by real-time adapting to local traffic. And we do this with a pilot project with simulated data in a city in China. So what is reinforcement learning exactly? So it's it's pretty up and coming last few years. So basically it's trial and error based learning. So I will use the game of chess as an example. So if you look at the figure on the right, there's an agent, let's say a chess player, and there's an environment, the chessboard. And every turn, the agent gets to see the board, the current state of the board, and decides to take an action. And based on this action, eventually it gets a reward if it has won or has lost. So, basically, with these rewards, it can eventually learn itself which actions are better than others. So in the game of chess, it's just 64 squares. So everything is pretty straightforward to apply reinforcement learning to. But traffic signal control is much more vague and real world. It's chaotic. So there's not really a principal source of data. So this research was about what is a good state, what is a good reward, what is a good action. For example, literature has used images, so camera from above, from in the intersection, to use as input, but it might be a bit too much data. You could also use maybe the sensors in the ground and just use counts of cars. So there's a lot of things to choose from. So on the next slide, you could see our algorithm in use. So this is just in a simulation. And here you see the cars passing by the intersection. You see the red and green dots that are the traffic lights. And basically, this is our reinforcement learning agent controlling the traffic lights after 1 day of training. And that the agent basically gets to see the amount of cars that are waiting in front of each traffic light, in addition to the amount of cars that are approaching. So it can actually learn to anticipate approaching vehicles. So you can see that it does a fairly good job of not getting any traffic jam. Actually, it does such a good job that if you can see the next slide, actually we get a reduction of 1/3 in travel time compared to state-of-the-art rule-based methods. So just to put this in perspective, if you apply this in large scale, for example, in the full city of Amsterdam, this has a very big impact, because instead of needing 45 minutes to get somewhere, it would only be 30 minutes. So this whole research was pretty much theoretical and academic, but the next step is to apply this in practice. Of course, there will be many philosophical questions to be answered, and there need a lot of restrictions, but we think it is the future and it's possible. And we can add, for example, we can give priority to bicycles, we can give priority to the public transport. And I think it will be a nice next step to try to apply this in the real world. So that was basically a short overview of the research project I was working together with the guys from the AI team. So thanks for listening.
Thanks, Sierk. So as I said earlier, I see two big groups of projects that we work on. This was an example of the more applied projects. And the second group is a little bit, how do I put this? They're projects that more reflect our values as a city and where we want to head as a city. Think about topics like diversity and fairness and privacy and inclusion, topics that raise also a lot of ethical considerations, a lot of interesting discussions. So for the next three projects, please do anything that comes to your mind as a citizen, also next to a researcher or data scientist or whatever you are in your everyday work life. Please put remarks there because we're really interested in your opinion. The first project was inspired by the idea, what if we could have interface where people could upload a picture of their neighborhood and see how would it look with less cars or maybe with more graffiti, and let them choose the city they want to live in. So Tom, please tell us more about your work and how you're tackling this problem.
Thank you, Eva. Hi, everyone. I'm Tom, and I'll be presenting about my thesis, which is about unsupervised object discovery and object insertion using generative adversarial networks. Since I only have a few minutes, I'll go into detail about a few things. I'll discuss with you the objective and the relevance of this project. I'll show my models and how it works for a bit, and I'll show some preliminary results as well. So right now we're usually making use of supervised learning, which means that we need annotated data, and that annotated data is specific for the task at hand and the domain at hand. But annotating images is very expensive because it's human labor, so it's costly in terms of time and money. So we would like to move to a more generic domain-independent approach, actually, because the municipality has a lot of data, but not necessarily a lot of annotated data. And that's where the unsupervised part comes into play. So I'm applying this on 2 tasks, basically. The first is object discovery, in which we try to find and discover objects in raw images without annotation and provide an object mask for those. And the second task is object insertion, where we want to insert a given object into a target image while it still looks realistic. And as Eva mentioned, we can use this for a few things. So policy visualization would be a goal of this, so that we could indeed add greenery or cars or persons or benches to street scenes, for example. And indeed, we could turn this into an interactive tool for citizens where they can play around with AI and envision their ideas for the city, basically. So the models that I'm using are based on adversarial learning. For the ones that are not familiar with this method, I'll explain it shortly. So what you see is a schematic overview of a generative adversarial network where 2 components learn from each other, basically. So we have a generator and a discriminator. And the task of the generator is to generate samples that resemble real samples. And the discriminator here tries to distinguish between the real samples and the fake samples, thereby giving feedback to the generator. And ultimately, the generator tries to fool the discriminator by generating samples that are indistinguishable from the real ones. So that's the methodology that I will use. The first model, which is used for object discovery, is called the copyGAN. And so it needs to discover and segment objects in an unsupervised manner. So in the figure, you see a source and a destination image, and we want to find and have a mask for the objects in the source image. And so the generator is tasked with copying objects from the source image into the destination image, yielding the composite. And afterwards, the discriminator will judge the composite, whether it's real or fake. And so all the way to the right, we see what we would like to see, namely that the object is copied into the destination image, making it look realistic. And the middle B column shows other solutions that do not work that well. So if we, for example, would copy part of the background or part of the object or the object with a sloppy cut, it would not yield a realistic looking image. So in this way, we try to teach the generator to only copy objects and cut them out nicely, basically. So that's the first model. The second model is the MoveGAN, which the goal of this model is to insert a given object in a target image, also in an unsupervised manner. And I try to, and it works by learning a conditional affine transformation, which is conditioned on the object and the target image. And this would actually be one of the first neural baselines for this, because right now we're usually making use of heuristics. And there are a lot of challenges in this. Think about scale, perspective, light, shadow. So it might be nice to have a learned approach for this that can handle those challenges. Combining these 2 models, we could have one big pipeline. I don't really have the time to go into detail, but what you can see here is that the copyGAN would be responsible for finding objects in some image, and the MoveGAN could then transfer those objects to other images, basically. Yeah, if there are any questions about this, ask them afterwards, please. I'll show you some results. These are on toy data sets, basically. So the resolution is also low, so it can be a bit pixelated. I'll come back about the more realistic data later. But this is more to check if the method can work, because this is all unsupervised, so there's no information whatsoever about the source images. But what you see is that the model is pretty capable of segmenting out the objects, basically. And on the next slide, we see the MoveGAN results. Especially the bottom example is interesting. Also, a toy example dataset is this. But the bottom example is interesting because the right side of the object is basically an edge, because it was to the border of the image where it came from. And the model here learns to insert the object all the way to the right, such that the edge of the object is again next to the border of the image. Yeah, which is the learned approach that you see. And then, so these are toy data sets. So this is to validate the method and see if it works. Right now, I'm working on applying this on more realistic data that's more similar to city data. So Coco and the cityscapes data set. And then for future directions and plans, it might be nice to add some conditions. So for example, conditional discovery, where we want to find specific object classes and have more control over the number of objects that we discover. But this is hard since we don't have that information embedded in the image. Yeah, so that was in a nutshell what I'm working on. Thanks for your attention. If you have any questions, please ask in the chat or Q&A. Thanks.
Indeed. Thanks, Tom. And then we move on to another GANS project. It was mentioned a little bit earlier, the topic about privacy, and Maarten was saying that we can only blur or remove the faces of people. We can also blur whole detected people to make sure that we don't recognize our neighbor by a sweater or so. But there are also other approaches we can take, and that is generate fake people. So Kaleigh is going to tell us a little bit more about that.
Yes, thank you, Eva. So yes, I'm working on a method of anonymizing people and images using generative adversarial networks. The motivation behind this project is to protect the privacy of people who appear in publicly available images, while also maintaining a realistic image. This is particularly important for municipalities that want to release images of the city for public use, but who are conscious of protecting the privacy of their citizens. For this task, I'm developing a GAN to replace real people with generated fake people while keeping the background of the image unchanged. Yeah, so here you see an overview of the model architecture, which I've adapted from the pedestrian synthesis GAN paper listed at the top. To start, we take an image and the bounding box coordinates of the target person. We then create a redacted version of this image where the bounding box is replaced with gray pixels, effectively removing the real person. This redacted image is sent to the generator, which outputs the generated image. The generator improves by evaluating this generated image using the background discriminator, the person discriminator, and the L1 loss, meaning that the generator loss is the sum of these three losses. So the purpose of the background discriminator is to push the generator into learning a more realistic background. It takes as input the redacted image and either the generated or original image and predicts if these two images are a realistic pair. The person discriminator is designed to push the generator into learning a more realistic person. It takes as input the cropped region containing the generated or real person and tries to determine if this person is real or fake. And finally, the L1 loss is used to push the generator towards the original image, which is useful for generating the background. Yeah, so next we see two examples of generated test images. Each example consists of three images. From left to right, we have the original, redacted, and generated image. These examples are some of the more realistic and detailed results we've gotten so far, especially with regards to the body shape and facial features. The examples on this slide are more typical results in that they generally look like people, but it's difficult to distinguish any features aside from body shape. They also illustrate the challenges associated with filling in the background surrounding the person, especially with regards to generating the yellow bag and the uneven curve in the bottom right image. Regardless, I think it's easy to see that the task of generating detailed people is more difficult compared to just filling in the background. So next, I'd like to note a few of the challenges we've faced. In addition to generating realistic-looking people and backgrounds, it's a challenge to generate good results consistently. If you compare the images on the right with the images from the previous slides, you can see that the same model can produce a wide range of results in terms of quality. Secondly, we also face challenges in dealing with more complex scenes, such as occluded or overlapping people, as well as various lighting conditions. And thirdly, choosing a reliable method of evaluation is often a challenge when working with generated images. We're currently evaluating our results qualitatively, but we will also consider additional methods. And there are also several considerations associated with the specific task of anonymizing people. First, it's important to ensure that the set of generated people reflects an appropriate level of diversity. For example, we want to make sure that the model doesn't generate all people with the same race or gender. Secondly, it's important to verify that the generated people are significantly different from the people in the training images. For this task, the last thing we would want is for the model to simply memorize people from the training data and then regenerate them in different images without our knowledge. So before using a model like this, we would want to develop additional methods for verifying that the results are being generated as we intended. Yeah, so that's my presentation. Eva, back to you.
Thanks, Kaleigh. And the big question, just because people are generated, does that mean that they don't deserve privacy? Who knows?
I don't know.
Indeed. So the last presentation we're going to hear about is about fairness. So this is a topic that we've been coming back to over and over again at the city. We've had already a bunch of graduation projects on this topic. We've looked into group fairness versus individual fairness. We've looked into causality. We've looked into a lot of things, but the one underlying problem that these approaches have is that they assume the pre-existing domain expertise and knowledge about sensitive attributes. And this year we decided to tackle the problem in a different way. So Selma will now tell us how to do that without the need of domain expertise.
Thanks, Eva. Hi, everyone. My name is Selma, and for the past 4 months, I've been working on a method to discover bias with clustering. So as we all know, AI technologies are increasingly impacting individuals, groups of persons, and the entire society. So as organizations, companies, and the governments, we need to ensure that the technologies that we use are fair, meaning that they don't discriminate against certain individuals or groups. And that's why I came up with this method to work on automatically detecting bias. So on the next slide, you see my objective, which is automatically detecting bias with clustering. And the main advantage with clustering is that you already automatically make groups from the data sets, and you don't need to predefine which kind of sensitive attributes are in your data set, or which kind of probably vulnerable groups are in your data set. The clustering does it itself. And one of the main advantages of this method is that it's model agnostic, since, as you can see here on the pipeline, what we feed the hierarchical clustering algorithm with are the results of the classifier or regression algorithm or any type of algorithm. So we only need the results of the algorithm to apply this clustering mechanism. So we feed it the attributes of the data set, the errors, the predictions, and the correct labels. And then this clustering algorithm splits the data set into 2 clusters, and then it continues to cluster, to split on the clusters using k-means. K-means algorithm splits the data set into 2 clusters, and then it calculates the performance of the persons and the performance of the cluster. So it uses performance metrics such as precision, but you can also select false negative rate, true positive rate, accuracy. So you calculate the performance of the cluster, and then you calculate the bias. And here we have the bias defined as the difference between the performance of this particular cluster and all the other clusters or data points. And the higher this difference is, the more it tells us about how biased this cluster is, because it means that the classifier produces substantially more errors or substantially less errors, meaning that it's either discriminating because it produces more errors when compared to the other clusters, or that it's favoring because it produces less errors when compared to the others. So once we've identified the biased clusters with the highest variance of performance, we can dive into it and see what makes this bias cluster so different, what makes the classifier perform different on those bias clusters compared with the non-biased clusters. And since we use k-means, we have access to the centroids. The centroids are essentially the center of each cluster, and they can function as a kind of summary of each cluster. So we can compare the centroids of the biased clusters with those of the non-biased clusters and see what kind of features, what kind of patterns we can see in the biased clusters that have caused the classifier to discriminate or favor this particular group of persons. There are several methods to analyze those bias clusters. It's still very much a work in progress, but it's really interesting because you can automatically detect those groups. You can use it and apply it on different algorithms. So you can apply this method on classification algorithms, but you can also use it on regression algorithms if you change your error metric to residuals, because then you can split it adequately. And you can also play around with different performance metrics depending on which kind of tasks you are using, applying those algorithms on, and which kind of performance metric is most important for your particular task. And still, we have some challenges with linking what we found about the bias clusters and the patterns within those bias clusters to fairness. So what does the bias cluster and the patterns within this cluster tell us about how fair the algorithm is working? And can we find any patterns or links from one another? So that are the current challenges that I've been working on. And lastly, my study is mostly focusing on detecting and discovering bias, but it's one thing to find the bias, and it's another thing to mitigate this bias and to prevent this algorithm from discriminating on certain groups of people. So that's also an exciting next step in this study. Thank you for your attention. I think that's it.
Thank you, Selma.
So there are a couple of questions that come in for Kaleigh from Koen. And what they would like to know is the AI reduces the average travel time, but what about standard deviation? Surely reducing the average but raising the amount of longest travel is not optimal. What quantity, the question is gone. What quantity is the focus of the AI? So
that's a very good question. That was something I was considering a lot at the start. For this research, the aim was just to reduce the average travel time, mostly out of a basic, just to make it a bit more basic. But yeah, and we also thought about it that if you don't want to decrease the standard deviation, you can basically say that if you're waiting and you have to wait quite long, then basically it's for the greater good. If it works very well, then you are this time the one that has to wait a bit longer than others. But next time you might pass quicker because the average travel time will be optimized. But of course, you can very well debate about this. And it's just an important issue, basically.
All right. Thank you very much for that, Sierk. I'd just like to say a big thank you to all of our speakers today. It's been a very informative and a very great presentation. I've personally learned a lot. So thank you very much for that. Thank you very much for our audience as well. I think this has been a really great webinar. So thank you. Please keep an eye out for our meetup page for any other events that we are going to be hosting in June. That was it for today. Thank you very much. All right. Bye-bye.